All right, this is the review sheet that I gave you. Again, it's not a completely comprehensive review sheet, but just to help you get some extra practice on problems. I did put an extra limit practice on Canvas with answers if you need that. Okay, so remember when you're evaluating a limit, the first thing you're going to do is you're going to plug in. Always, 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 always. Okay? So here we're going to plug in our 4. So we're going to get negative 2, 4 squared, minus 4, plus 1. And that's going to give me negative 32 minus 4 plus 1. And that's going to give me negative 36 plus 1, so negative 35. All right, so on this one, we're going to plug in 3 pi over 2. And so that's going to be cosine of 3 pi over 2 minus 2 over sine of 3 pi over 2 minus 1. The cosine and sine, I'm going to go up here, of 3 pi over 2, that's down here, so 0, negative 1. So cosine is 0 and sine is negative 1. So 0 minus 2 over negative 1 minus 1 ends up being negative 2 over negative 2. So the limit is just 1. Number 3, we're going to plug in 9, and we end up with 0 over 0. So we know that that's not good, and there's something else that we can do. And this looks to be one that we're probably going to end up factoring. So x plus 9, x minus 9 in the numerator. And on the bottom, things that multiply to give me negative 27 at the same time add or subtract to give me negative 6. So negative 9 and plus 3. So my negative 9, x minus 9s, are going to cancel out. And I have the limit of x plus 9 over x plus 3 as x approaches 9. So I'm actually going to plug in my 9 now into what's left over. And that's going to give me either 18 over 12, that would work, or you could simplify it to 3 over 2. Doesn't really matter. You don't have to simplify it. All right, for part D, we have 0. We're going to plug that in. We end up with 0 over 0. So we know there's something else we can do. And again, it kind of looks like I can factor the denominator, so let me try that. So I've got limit as x approaches 0, 3x squared, x squared in the denominator, and I've got x plus 5 left. Okay, so x squareds could cancel in the numerator and the denominator. And then I have 3 over x plus 5. I should be able to plug in my 0 now, and I'll get 3/5. So all of those are examples of ones that we can just plug in. Uh-oh, my bad, didn't mean to do that. And figure out the answer. I'm guessing I'm not going to be able to move this over. Okay, so I managed to move this over, but I had to erase all the other stuff. That's fine. Hopefully you already got that. Okay, so now we're on part E, and we're going to plug in 9, and we're going to get 9. Square root of 9 is 3. 3 minus 3 is 0 over 0, so that's a 0 over 0. So we know that there's something else that we can do. It's a square root, so probably a conjugate is going to be what I need to do. So I'm going to multiply by square root of x, plus 3 over square root of x plus 3. And so when I do that, I'm going to have the limit as x approaches 9. In the numerator, I'm basically going to FOIL. Square root of x times square root of x is x. These are going to cancel. 3 square root of x, negative 3 square root of x, those cancel. Minus 9 over, in the denominator, x minus 9 times square root of x plus 3. Now notice I didn't multiply the denominator because I know that I'm going to be able to cancel something out, which in this case is the x minus 9. So now I'm going to have the limit of 1 over the square root of x plus 3 as x approaches 9. I should be able to plug the 9 in now and get an answer. So square root of 9 is 3 plus 3, so that's 1 over 6. So my answer is 1 over 6. The next one, we're going to plug in the number 2. So when we plug in 2, we get, I'm sorry, I misread that. It's a negative 2. So that's going to give me 10 over 0. What that means is that you have a vertical asymptote at negative 2. So when you have a vertical asymptote, you have to check the limit from the left and the limit from the right. So you have to check a number that's to the left of negative 2. And so when you do that, remember, you're just looking to see, is it going to be negative infinity or a positive infinity? So when you plug in negative 2, I'm sorry, a number less than, to the left of negative 2, like negative 3, that's going to give you a positive 15 over a negative 1. And so as you continue to plug in numbers, it's going to become closer and closer, or getting out further and further away, so it's going to be negative infinity. You're going to do the same thing as you're approaching negative 2 from the right. So plug in maybe like negative 1 or something like that. And so when you do that, you end up with a positive on the top and a positive on the bottom, no matter what number you plug in, and you end up with a positive infinity. So what that tells me is when I'm going from the left, I'm going down on the asymptote, on the left side of the asymptote, and up on the right side of the asymptote, which tells me that the limit as I approach negative 2 does not exist. It's going in two different directions. So at negative 2, here's my picture, I'm going down this way, but up that way. So it does not exist at negative 2. It's going the same direction in both, then you can say it's positive infinity or negative infinity. Okay, the last one, we're plugging in infinity. So anytime I see if I'm approaching infinity, the first thing I'm going to remember is that I'm going to have to look for something about horizontal asymptote rules, like top heavy, bottom heavy, or balanced. In this case, it makes my life so much easier that it's balanced. Remember, if it's balanced, you just put the coefficient of the top over the coefficient of the bottom, and you can simplify it if you would like. So the answer to that one's just 1/2. Okay, I'm going to go ahead and record this page. It's kind of silly, I feel, just because you can look at the picture, but just in case you need an explanation of something, it's just hard for me to point to the picture when I'm on my iPad, but I'll do the best I can. Okay, so we have the limit as x approaches negative 4 of f of x. Remember, that is a two-sided limit. So what that means is I have to check the left and the right. So when I'm coming from the left side of negative 4, I'm getting closer and closer to 3. When I'm coming from the right side of negative 4, I'm getting closer and closer to negative 2, which means the limit does not exist. It's a jump discontinuity, all right? I guess I could erase my stuff on my picture as I go. Okay, next, f of negative 4. So when x is negative 4, what's y? We have a closed-in circle up here at 3, so that's my answer, 3. Okay, that just means the actual point, and that's the only closed-in dot, okay? Is f continuous at x equals negative 4? Question mark on the next line. Okay, so is it continuous? No. We already said there's a jump there, okay? The limit does not exist at negative 4. And remember our three things that we're going to list on the next page, actually. The limit has to exist, f of negative 4 has to exist, which is true, but the limit doesn't exist, so therefore it's not continuous. Okay, the limit as I approach negative 1. So as I get closer and closer to negative 1 from the left, I get closer to 4. From the right, I also get closer to 4, so the limit is 4. F of negative 1 is 4. So is the function continuous at negative 1? Yes, because the limit exists. F of negative 1 exists, and they are equal to each other. So that's the reason, okay? The next one we have positive 2. So when I'm getting closer and closer to positive 2 from the left, I'm getting closer to negative 1. When I'm getting closer and closer to positive 2 on the right, I'm getting closer to 5. So the limit does not exist. F of 2, however, is negative 1, because it's down here as a closed-in circle. Is it continuous at 2? No, and the reason is the same reason as part C. The limit did not exist at 2. So it cannot be continuous. All right, the limit as I approach 4. So as I get closer and closer to 4 from the left, I get closer to 2. From the right, I also get closer to 2. So the limit is 2. F of 4 does not exist, though, because there's no closed-in circle anywhere on 4. So is it continuous? No. F of 4 does not exist. So therefore, can't be continuous, okay? All right, for the function f of x equals 3x plus 9 over x minus 5, find the horizontal asymptotes, find the vertical asymptotes. So this is just a reminder of how to do these. Remember, horizontal asymptotes, you've got the rules, like bottom heavy, top heavy, balanced. So this is a balanced. X to the first on the top, x to the first on the bottom, so it's balanced. And that means that our horizontal asymptote is at y equals 3 over 1, or just 3. Okay, this isn't asking me to find the limit, it's just saying what's the horizontal asymptote. Now vertical asymptotes, we did these when you guys did the matching card activity. Okay, we talked a little bit about reminder of how to do the vertical asymptotes. Basically, you set the denominator equal to 0 and solve. Okay, so take the denominator, And I know you can do that in your head and solve. And that's where there is a vertical asymptote. So you won't have any values at 5. Okay, I told you before this question will be on your test. So you do want to make sure you know how to do number 4. You can just look it up. The main 3 things you need to have are that the limit as x approaches a of f of x exists. On my key in parentheses, I also have the limit from the left equals the limit from the right. You can include that if you want, but it's not required. You have to know, though, that this is a two-sided limit. So that means I need to check the left and the right, okay? Number 2, I don't know why I'm moving here, but okay, hold on. Okay. F of a exists. That has to be true. And then the last thing is that the limit as I approach a has to equal f of a. All right. So not only does the limit have to exist and f of a has to exist, but they have to equal each other in order for the function to be continuous at that particular value. Okay. We're going to do that right here in this problem. It asks us for what values of x is the piecewise function continuous. Now, since they don't tell us which ones to check, you want to check everywhere that something happens on the graph. So at 0, it switches equations, at 1, and also at 2. So you want to check those 3 places. So we're going to start with 0. X equals 0. We want to check the limit from the left as x approaches 0 from the left. And that is our top function, cosine of x. So cosine of 0, and the cosine of 0 is 1. Okay, the limit as I approach 0 from the right. Okay, so I'm going to use the second equation, 3x squared plus 1. So 3, 0 squared plus 1, that's going to give me 1. Then I have to try f of 0. F of 0, I'm going to plug into the second equation again because it's where where x is equal to 0. So it's still going to be 1. And so what that tells me, since the limit exists, f of 0 exists, and they are the same, it's going to be continuous. I'm not going to write all that because I don't really have room, but that's the reason. Okay. I'm going to do the same thing at 1. At x equals 1, I'm going to check the limit. I'm going to write up here as x approaches 1 from the left. So as I check the second piece of the function is what I was trying to say before I somehow turned off my recording. Okay, so I've got the limit of f of x as x approaches 1 from the left. That's going to be the second piece of the function. So 3 times 1 squared plus 1. So that's going to be 4. Then I'm going to check from the right. Side of the function, which is going to be the third piece. So it's going to be negative 1 cubed minus 2. Remember, you are going to show that. And that's actually negative 3. So the limit does not exist. So that tells me that it is not continuous at 1. I'm not going to write that, but that's what it means. Okay, x equals 2. Same thing. Limit as I approach 2 from the left. So that's this top piece of the function, or I'm sorry, the third piece, negative x cubed minus 2. So negative 2 cubed minus 2. And that's going to give me negative 10. Then I'm going to check the limit as x approaches 2 from the right. And that's going to be the last piece of the function. So negative 2 to the 4th is negative 16. Obviously, the limit does not exist. So therefore, our function is not continuous at 2. All right. So this is similar to one of the multiple choice questions that's on the AP sample questions. So you can check that. You can do one of those again. All right, now for number 6. There we go. That's much better. I know y'all probably can't see it as well, but at least I can write better. Okay, so on number 6, it says find the value of k that makes the function below continuous everywhere. So remember, the first thing you want to do is you want to check the limit from the left. And we're going to the left of pi, okay, and check the limit from the right of pi. Okay, so when I check the limit from the left, that's this equation here, negative 2 cos x. So negative 2 cos x. So I'm going to plug in pi. So that's going to be, and put it down here, negative 2 cos pi. The cosine of pi is negative 1. So negative 2 times negative 1 is 2. Then I'm also going to do that for the right side of pi, which is this equation, 3k sine x over 2. So I'm going to plug in, I don't know what k is, but I'm going to plug in pi in place of 2. In place of x. So the sine of pi over 2 is 1. So it's going to be 3k times 1, or 3k. Now, in order for it to be continuous, the limit from the left has to equal the limit from the right. That's one of the things that the limit has to exist. So I set 2 equal to 3k, and that gives me k equals 2/3, and that's my answer. Okay, and you can also check f of pi, but you should get the same thing when you plug in your 2/3. Okay. Number 7, if you plug in the number 1, so let's read this because it is a little confusing. Suppose f of x equals this ugly function for x not equal to 1. So in other words, we can't plug in 1 because we have this x minus 1 in the denominator. We can't divide by 0, okay? And f of 1 is equal to c. For what value c is f continuous? Well, if something's continuous, I would like to find the limit first, okay? And I'm going to find the limit of this function. Now, if you plug in the number 1, you end up with 0 over 0, because it's square root of 5 over minus square root of 5 over 1 minus 1. So we're going to have to do the conjugate. So it's going to be 2x plus 3 plus the square root of x plus 4 over square root of 2x plus 3 plus the square root of x plus 4. In the numerator, you're going to FOIL. Square root of 2x plus 3, square root of 2x plus 3, multiply those, and then the middles cancel, and then multiply these the last two. So limit as x approaches 1, 2x plus 3 minus x plus 4. In the denominator, I'm not going to multiply. I'm just going to leave it the way it is. And hopefully I'll be able to cancel something. Usually I can. Okay, now in the numerator, I have 2x plus 3 minus x plus 4. I need to distribute this negative. Okay, I'm just going to write my numerator out here. 2x plus 3 minus x minus 4. Simplify that, combine like terms, you get x minus 1. So in the numerator, I now have x minus 1. I also, notice, have x minus 1 in the denominator. Okay? So obviously my x minus 1s are going to cancel, and I'm going to be left with 1 over the conjugate. So I now have the limit as x approaches 1 of 1 over the square root of 2x plus 3 plus the square root of x plus 4. Plug in 1, and you get 1 over the square root of 5 plus the square root of 5, which is 1 over 2 square roots of 5. Okay? Now, what they're actually, I'm just move this up over those problems, but that's okay. What they're asking me is, for what value of c is f continuous at x equals 1? So in other words, when you plug in 1, you should get a c value. And I just figured out what the c value is. So let me write that down. In order to be continuous, okay, the limit has to exist, which it does. F of 1 has to exist, and they have to equal each other. And I just figured out that the limit has to equal 1 over 2 square roots of 5, which means f of 1 also has to equal 1 over the 2 square roots of 5. So c is equal to 1 over 2 square roots of 5. So they have to equal each other, which is the definition of continuity. All right, last page. Number 8, the table of values below is for the continuous function q of x. Explain how you know the graph of q of x crosses the x-axis at least once. Okay, the reason for this is the intermediate value theorem, which you can abbreviate IVT. You do need to say something about q of x being continuous. So I'm saying since q of x is continuous and q of -1 equals -6.4, and q of 0, sorry, my 4 is ugly, equals 2.7, the function, the function must have crossed the x-axis between, sorry, I'm getting uglier here as I write, q of -1 and q of 0. Okay. In order for the limit of f of x as x approaches a to exist, what must be true about the limit from the left and limit from the right? We know that they have to be equal. So the limit from the left has to equal the limit from the right in order for the limit, the two-sided limit, to be true. I'm really and truly not sure how I keep doing that, y'all. Sorry. Okay. Number 10. Suppose a function f has the following characteristics. Okay, they tell us that f of negative 4 is equal to negative 2. They tell us the limit as x approaches 4 from the right is negative 2. They tell us that f of 3 is 4, and the limit as x approaches 3 is 4. Okay, circle all of the statements that are definitely true, just given this information. So f is continuous at negative 4. In order to figure out if something's continuous, we would need to know the limit from the left, the limit from the right, and f of negative 4. We know the limit from the right, and we know we know f of negative 4 is negative 2. Those are the same, but we don't know the limit from the left. So that's definitely, we don't know. It's not definitely true, okay? Part B, the limit as x approaches 4 exists. Again, same kind of thing. We know the right, but we don't know the left, so we can't say for sure that it exists. F is continuous at x equals 3. Well, if the limit is 4 and f of 3 is 4, then we know that it is continuous at x equals 3. And if the limit, the two-sided limit, which is what this is, exists on number 4, that's the two-sided limit, then we know that the left must exist. So the left and the right both have to exist, okay? The 4 trig limits that you have to memorize, you can look them up, but I'll write them here. The limit as x approaches 0 of sine x over x is equal to 1. The limit as x approaches 0 of sine ax over x is a. Going in a little different order than when I wrote it down on my key. The limit as x approaches 0 of sine ax over sine bx is a over b, excuse me. Now this one is the one, it's a cosine. We did two different ones. We did one that was 1 minus cosine and one that was cosine x minus 1. It really doesn't matter because they're both 0. We wrote that on our little graphic organizer on our yellow sheet. So you can look that up. But they're the same. Okay, so those are the 4. Remember, please notice all of these limits are going to as x approaches 0. These only work if x approaches 0. Okay, the last one, it's easy. It looks like it's complicated, but it's really not. So what they're asking you to do is they're saying we have a limit as x approaches a of f of x is negative 10, and we have the limit as x approaches a of g of x is 5. Use the limit properties to solve each of the following. So we have the limit of f of x over g of x, okay? Basically what that means is I can split these up and have the limit of f of x over the limit of g of x. And I actually already know both of those because they gave them to me. So negative 10 divided by 5 is negative 2. A is negative 2. That's really all you're doing. On part B, it's a times. So you're going to multiply. Negative 10 times 5, negative 50. This is a subtraction. So it's going to be negative 10 minus 5, so negative 15. See, those were a lot easier than you thought.